Можно? Well, today our first goal is to discuss the continuous functional calculus in C-star algebras. So suppose we have a unital Banach star algebra, A, unital Banach star algebra, and a normal element little a. So let's recall that normal means that A commutes with A star, with a joint. So roughly, the continuous functional calculus is a tool of giving precise meaning to the expression f of a, where f is a continuous function defined on a suitable subset of the complex plane. Well, of course, we already know what f of a is in the case where f is a polynomial. And it's rather easy to extend this definition to the setting where f is a holomorphic function on the complex plane. So we simply decompose f in the Taylor series and substitute a instead of the variable. And we get an element in our algebra. A typical example is the exponent, which you, of course, you know about from your, for example, from your differential equations course. So our goal is to extend this construction to more general continuous functions, which are not necessarily given by power series. Well, let's introduce some notation. Suppose we have a compact subset K of the complex plane. And let little t denote the standard coordinate on K, that is just the inclusion map of K into the complex plane. By definition, continuous functional calculus, calculus for little a on K, on this compact set, is a continuous unital star homomorphism, gamma A, from C of K, from the algebra of continuous functions on K, to A, such that this homomorphism takes little t to A. By the way, it's clear from the definition why we assume that A is normal, because if A is not normal, then there is no way of defining such a map, because little t is, of course, normal. It sits in a commutative algebra. And so the range of a homomorphism from a commutative algebra, of a star homomorphism from a commutative algebra to another star algebra, obviously consists entirely of normal elements. Okay, of course this definition just describes some property of this gamma. In particular, it's not immediate from the definition that such a homomorphism exists. By the way, a few words about the terminology. The word continuous here, when I say continuous functional calculus, the word continuous here refers not to the continuity of this map, but rather to the fact that it is defined on the algebra of continuous functions. For example, if we replace here the algebra of continuous functions by the algebra of holomorphic functions, then we get a holomorphic functional calculus. Here is a simple necessary condition for the existence of such calculus. So suppose gamma exists, then K necessarily contains the spectrum of A. And moreover, if it exists, then it is unique. Gamma is unique. This is a rather simple observation. Property 1 is true because any star homomorphism reduces the spectrum, and the spectrum of little t in C of k is precisely k. So we must have this inclusion. And the uniqueness is easily deduced from the Stone-Weierstrass theorem, which implies that the star subalgebra in C of k generated by T is dense. So it is uniquely determined by gamma of T. And gamma of T is A. How about the existence? Well, it turns out that if A is a C-star algebra, then this necessary condition is also sufficient. And we have the following result. Suppose that A is a unital C-star algebra, and little a is a normal element. Then, for every compact subset of the complex plane, such that K contains the spectrum of A, there is a unique continuous functional calculus gamma A for A on K. And moreover, if K is exactly the spectrum, if K equals the spectrum, then this gamma is actually an isometric star isomorphism. Isometric star isomorphism of the algebra of continuous functions on the spectrum onto the C-star subalgebra of A generated by A and the identity. So let's recall that this is the smallest C-star subalgebra of A containing A and the identity. A rough idea of the proof is as follows. We, first of all, everything can be easily reduced to the case where K is exactly the spectrum, because, well, if K is bigger than the spectrum, and if we have a functional calculus on the spectrum, then we can just compose it with the restriction map from C of K to C of sigma of A. So it suffices to prove the theorem in the case where K is exactly the spectrum. So in this case, we let B denote this C-star subalgebra of A, generated by little a. It is obviously commutative. It is commutative, so we have the Gelfand-Neinberg theorem, which tells us that the Gelfand transform of this algebra is an isomorphism onto the algebra of continuous functions on the spectrum. And as for the spectrum, the maximal spectrum of this algebra, it is actually homeomorphic to the spectrum of little a. And the homeomorphism is just essentially the Gelfand transform. It takes every chi to a hat of chi. So the Gelfand transform of little a is a homeomorphism of the maximal spectrum of B onto the spectrum of A. So now the functional calculus for our element can be constructed as follows. First of all, this homeomorphism phi induces an isometric star isomorphism between the algebra of continuous functions on the spectrum of our element and the algebra of continuous functions on the maximal spectrum of B. And this is an isometric star isomorphism. But here we have the Gelfand transform from here to here, which is an isomorphism by the Gelfand-Neinberg theorem. So we take the inverse map to gamma. So B is contained in A, and the composition of these maps is exactly what we are looking for. This is the functional calculus for A on the spectrum. So this is the idea of the proof. Well, I don't.
Space is an absolute attract, and spectrum is should be the union of disks.
Well, in my view, this is if this is true, but even if this is true, I'm not sure that this is the real reason for for this result for this result. The real reason is hidden here. So if gamma is not an isomorphism, we're not an isomorphism, then we don't have this arrow. And so the point is that gamma is an isomorphism, so we can take the inverse map. In my view, this is the real reason why this theorem is true. So this is the idea. Let's also observe that if, for example, f is a polynomial of one variable, then of course, if we restrict f to our set k and then apply the functional calculus, what we get is just f of a. For the simple reason that gamma is an algebra homomorphism, it takes t to a, so it takes f to f of a. And even more generally, if we have a polynomial f in two variables, x and y, then we can define a function, let's denote it by f tilde, on the complex plane, which takes every point z to the following number. Just substitute z and the complex conjugate to our polynomial. And then in this case, if we again restrict f tilde to k and apply our functional calculus, what we get is obviously f applied to a and a star. Again, for the simple reason that gamma is a star homomorphism. So in other words, this is f tilde applied to a. And this simple observation naturally leads to the following notation. Usually, instead of writing gamma a of f, we write f of a for every continuous function f on the spectrum of a. So this is convenient. This is a convenient notation, and it is compatible with the situation where f is a polynomial. Okay, let's look at two simple examples. I'd like to stress once again that in the general case, there is no hope to obtain an explicit formula for the functional calculus because, well, the gamma inverse is a rather inexplicit map. So we know that this map exists by the Griffin-Neinberg theorem, but we don't have a concrete formula for the inverse of this map. But in concrete situations, the functional calculus can be constructed by hand. For example, if A is the algebra of continuous functions on the compact Hausdorff space X, then for every element A of our algebra and for every continuous function f on the spectrum, it's rather easy to see that gamma of f, or f of A, is just the composition of f and A. This is immediate from the definition of the functional calculus. And another simple but classical example from operator theory is the case where our algebra is the algebra of bounded operators, and we apply functional calculus to a multiplication operator. So more exactly, we take a measure space, x mu, a sigma finite measure space. We take an essentially bounded measurable function phi on x, and we consider the multiplication operator m phi, which acts on L2 by the following simple formula. It takes every function psi to the pointwise product of phi and psi. So in this case, our algebra A is the algebra of bounded operators on L2. Then it's a standard exercise in functional analysis to show that for every continuous function f on the spectrum of this multiplication operator. And the spectrum, by the way, the spectrum of this operator is the essential range of f of phi. So we have the following formula. F applied to m phi is just the multiplication operator corresponding to the function f composed with phi. Again, this can be easily deduced from the definition. A little delicate point is here. So we have to give a precise meaning to this composition, because formally f is not defined on the range of phi. It is defined only on the essential range, which is somewhat different from the range of phi. Nevertheless, this function is defined almost everywhere, and this operator is well defined. Okay, let's now look at two simple but important properties of the functional calculus. Proposition. Again, we assume that A is a unital C-star algebra. Little a is a normal element of A. And we suppose that f is a continuous function on the spectrum of A. Then, first of all, we have the so-called spectral mapping formula. Spectral mapping formula, or spectral mapping property, which tells us that for every continuous function g on the spectrum of f of A, of course, we can apply. This is a rather different property. So first of all, what is the spectrum of f of A? The spectrum of f of A. So we know what is it in the case where f is a polynomial. If f is a polynomial, then we have the following formula. And it turns out that the same formula holds for every continuous function f on the spectrum, which is quite useful. And the second property is the superposition property. Superposition property, which tells us that if we take a function g on the spectrum of f of A, then of course we can apply g to f of A. So first we apply f to A, and then apply the functional calculus again, but now to the element f of A, and we obtain g of f of A. So the superposition property is that we have the following formula. So we can first compose g and f, and then apply it to A. Well, both results are rather simple. The first follows from the fact that gamma is an isomorphism of this algebra onto this algebra. And this is this closed star subalgebra in A, so it is spectrally invariant. And this easily leads to this equality. And the second equality easily follows from the fact that if we fix a little f and consider the right-hand side of this formula as a function of g, so this is a map which takes g to g of f of A, then this map satisfies just the definition of a continuous functional calculus. So it is necessarily, by the uniqueness, it is the same as the functional calculus for f of A. And so that by the uniqueness, we have this equality. What happens if our algebra is no longer unital? Sometimes this is useful in non-unital case. So suppose that A is a C-star algebra, not necessarily unital, and little a is a normal element of A. So in this case, we just embed A into its unitization, A plus, and we take the non-unital spectrum of A, which is, let's recall that this is just the spectrum of A as an element of the unitization. Let's also recall that the non-unital spectrum always contains 0. So A plus is unital. We already have a functional calculus for unital sister algebras. So for every element, for every continuous function f on the non-unital spectrum of A, the element f of A is well defined. But in general, this element sits in the unitization of A. So the natural question is, well, we want this element to belong to A itself. When is it true? And this is true. This is a simple exercise. This is true if and only if f vanishes at 0. So now we just can draw the following picture. We denote by M0 the ideal in the algebra of continuous functions on sigma prime of A, which vanish at 0. And then we have a functional calculus for our element A, which takes this algebra to the unitization of A. Again, A. And we can restrict it to this ideal M0. So this exercise implies that the restriction to M0 takes this ideal to A. So this is what we get if A is not unital. So the functional calculus is well defined, but it is defined only on those functions which vanish at 0. Okay, let's now apply functional calculus to study of positive elements in sister algebras. Positive elements. So suppose that A is a sister algebra, and little a is an element of A. We say that little a is positive, and use the following notation. If it is self-adjoint, and the spectrum of A is non-negative. Of course, in the unital case, I can remove the prime here. If A is unital, then this is equivalent, this condition is equivalent to the inclusion of the spectrum in the non-negative numbers, because as we know, the only difference between these two spectra is 0. Well, probably it would be more natural to call such elements non-negative, but nevertheless, this is the standard terminology. Usually we call it positive. Well, here's a simple example. If A is the algebra of continuous functions, or better, continuous and vanishing at infinity functions on a locally compact Hausdorff space X, then an element A is positive in the sense of this definition, if and only if this function is everywhere non-negative. Well, indeed, it is self-adjoint, if and only if it is real, and its spectrum is the closure of its range, so we have this equivalence. Morally, if we interpret sister algebras as non-commutative analogs of topological spaces, or non-commutative analogs of algebras of continuous functions, then self-adjoint elements correspond to real functions, and positive elements correspond to non-negative functions. It's convenient to introduce a special notation for this set of all positive elements. let's denote it like this. Well, this is a subset of A. But in fact, this is not just a subset. This subset has some special properties. So we have the following theorem. The set of positive elements is a closed convex cone in A. This means the following. If A is little a is positive and lambda is a non-negative real number, then lambda A is also positive. Second, this set is stable under taken sums, so if you have two positive elements A and B, then A plus B is also positive. So 1 and 2 also imply that this set is convex. Also, if an element is positive and, let's say, negative, then it is 0. And finally, this set is closed. The set of positive elements is closed in A. Well, just a few words about the proof. Properties 1 and 3 are rather easy. They easily follow from basic properties of the spectrum. For example, to prove 3, we just observe that if A is self-adjoint and its spectral is positive and negative at the same time, then its spectrum is 0. So its spectral radius is 0. But for a self-adjoint element, the spectral radius is the norm. So the norm is also 0, and so the element is 0. 2 and 4 are a little bit more involved. The idea of proving 2 and 4 is the following. We take the closed unit ball in A and intersect it with the set of positive elements. So to prove that 2 and 4, to prove properties 2 and 4, it's enough to prove that this intersection is closed and convex. Then from this it easily follows that we have 2 and 4 at the same time. And it turns out that this intersection can also be written in the following form. And the right-hand side is obviously closed and convex. And this equality is true by the Gelfand-Nalbach theorem. We simply take little a and generate a commutative C-star algebra. So a little a is self-adjoint. So this is a C-star algebra generated by this element is commutative. And observe that for the algebra of continuous functions on a compact space, this equality is more or less clear. So a function in the unit ball, a real function in the unit ball, so it is somewhere between -1 and 1, is positive, even only if we have this inequality. And that's it. The following result describes some basic properties of positive elements. First of all, if we have a C-star algebra homomorphism from A to B, a C-star algebra homomorphism, then it always takes positive elements to positive elements. Well, this is clear because it takes self-adjoint elements to self-adjoint, and it always reduces the spectrum. So by the definition of a positive element, it takes positive elements to positive elements. A useful special case is about the functional calculus. So if we have if A is unital, if A is unital and little a is a normal element of A, and if f is a continuous function on the spectrum of A, which is non-negative, then the element f of A is positive. This is just a special case of 1. We simply apply 1 to the functional calculus of A.
Can you please say again about this idea?
Mm-hmm.
In order to use Gelfand and Naimark, we need a commutative sister algebra, right?
Yeah.
And where do we get this commutative?
We just fix an element little a, and we want to show that it satisfies this condition if it sits here, if and only if it sits here. So it is self-adjoint. This element is self-adjoint from the very beginning. And we generate a commutative C-star subalgebra by this element. So the C-star subalgebra generated by a self-adjoint element is commutative.
Okay.
So we simply, so everything is reduced to this commutative C-star subalgebra. And it is isomorphic to C of x. Well, for convenience, we can assume from the very beginning that A is unital, because if it is not, then we simply join the identity. So it is just C of x. And in the algebra of continuous functions on a compact space, this equality is just a property of continuous functions. Okay, property 3 is about square roots. If A is a positive element of A, then there exists a unique positive element, little b, such that b squared equals A. And namely, b is nothing but the square root of A. So here we just apply the functional calculus, take the function square root and apply it to A. This makes sense because A is positive and the square root is defined on the positive half line. So this property is clear, and as for the uniqueness, well, the uniqueness is a little exercise. Again, which involves some properties of the functional calculus. Property 4 tells us that every self-adjoint element can be canonically decomposed as a difference of two positive elements. More exactly, for every self-adjoint element little a, there is a unique pair, A plus and A minus, of positive elements such that A equals A plus minus A minus, and such that the product of A plus and A minus is 0. And again, these elements are constructed quite explicitly by the functional calculus. Namely, they are obtained from A by applying the following two functions, t plus and t minus, where t plus and t minus, well, I'll not write explicit formulas, I just draw their graphs. This is t plus, and this is t minus. So we simply apply these two functions to A, and we get our elements A plus and A minus. And it's clear that they satisfy all these conditions. Again, a little exercise here is to prove the uniqueness of such a pair. This is some manipulations with functional calculus. And finally, a very important property 5, short but important. This result is due to Kaplansky. And it tells us that for every element in A, the element A star A is positive. Why is it important? Well, actually, this property historically this was not a theorem, but this was a part, this was an axiom. This was a part of the definition of a sister algebra in the original paper by Gelfand and Nymark. They also conjectured that probably this property follows, this axiom follows from other axioms of a sister algebra, but they were unable to prove it. And this was an open problem for about, for exactly 10 years. So Gelfand-Nymark's paper was published in 1943. So in 1953, Kaplansky proved that this is indeed the case. So this property follows from the sister algebra axioms. By the way, the proof of this fact is short, but it's quite tricky. So I can't explain it in a few words. This is just some series of algebraic tricks with, involving the functional calculus. By using the notion of a positive element, we can now define an order relation on the set of all self-adjoint elements in A. Namely, if we have two self-adjoint elements, A and B, in our algebra, we say that A is less than or equal to B if B minus A is positive. And we have the following result. First of all, I claim that this relation makes the set of self-adjoint elements into an ordered vector space. An ordered real vector space. Moreover, this space is positively generated by the positive cone. This means that first of all, it's a partially ordered set. A partially ordered set under this relation. Second, this relation is compatible with the additive structure in the sense that if we have two elements, A1 and B1, and another two elements, A2 and B2, satisfying these conditions, then A1 plus A2 is less than or equal to B1 plus B2. And also the order relation is compatible with multiplication by non-negative numbers. Numbers if A is less than or equal to B, and lambda is a non-negative real number, then lambda A is less than or equal to lambda B. Moreover, this order relation is somehow related to the multiplicative structure on A. So property 4, if A is less than or equal to B, and X is an arbitrary element in A, then we have the following inequality. Also, let's now recall that A has a norm, and the norm on A is also compatible with the order relation in the sense that if we have two positive elements A and B, and A is less than or equal to B, then the norm of A is less than or equal to the norm of B. So in some sense, the norm is monotone on positive elements. Property 6. Property 6 is that if A and B are invertible, and A is positive, invertible, and A is less than or equal to B, then B inverse is less than or equal to A inverse. Oh, by the way, I forgot to explain what I mean when I say that it is positive generated by the positive cone. Let me insert it here, 3 1/2. we have the following equality. So every self-adjoint element is the difference of two positive elements. Actually, this was already noted in the previous theorem. Every self-adjoint element is a difference of two positive elements. This means that it is the set of self-adjoint elements is positively generated by the set of positive elements. And finally, another useful property, property 7, is that if A is positive, then A is less than or equal to the identity in the unitization of A, if and only if it is in the unit ball of A. And if A is unital, this is equivalent to say that A is less than or equal to 1. This is true if A is unital. Well, just a few words about the proof. Properties 1, 2, 3, and 3, 1/2 are quite immediate from the properties of positive elements, namely from this theorem and from this theorem. Well, property 4 follows from the existence of the square root. We take the element b minus a and take the square root. And as a result, we see that if we write the difference of this element and this element, it can be written in the form C star C for a suitable element C. And by Kaplansky's theorem, C star C is positive. And the remaining parts are some combinations. The proof of the remaining parts is a combination of properties of positive elements with the Gelfand-Nyberg theorem. For example, if we want to prove property 7, we simply apply the Gelfand-Nyberg theorem to the C-star subalgebra generated by A and the identity. Well, in this case, we are in this case where A is just the algebra of continuous functions, and it's clear that a non-negative continuous functions is less than or equal to 1, if and only if its norm is less than or equal to 1. So it's kind of trivial. Okay. By the way, a useful corollary, not from this theorem, but rather from the existence of square root. Let me write it down here. Corollary of 3. If we have a bounded operator T on the Hilbert space, then it is positive as an element of B of H, if and only if the inner product of Tx and x is non-negative for every x. This is a useful positivity criterion for a linear operator. So the idea is that, well, the non-trivial part is here is to show that if T is positive, then this inner product is non-negative. So we simply take the square root of T, denoted by S, and observe that this expression is nothing but the inner product of Sx by itself. So it is non-negative. Okay, let's now talk about approximate identities in C-star algebras. So, morally, an approximate identity is an analytic substitute for an identity in a non-unital algebra. So if you have a non-unital algebra, then it is not always useful to take the unitization. Sometimes we have to work in the algebra itself. And in this situation, approximate identities are quite helpful. So let me, first of all, to begin with, let's briefly recall some definitions related to nets in topological spaces. Suppose we have a poset, a partially ordered set lambda, and then we say that lambda is directed, a directed set, if it satisfies the following conditions. For every two elements lambda and mu in this set, there is another element nu which dominates both lambda and mu. Here are two typical examples to keep in mind. First of all, of course, the set of natural numbers with the usual order is directed. And more generally, any well-ordered set is, any totally ordered set is directed. Another example, which is also quite useful, we suppose that X is a topological space, little x, and little x is a point in X. And we denote by lambda the set of all neighborhoods of this point. And this is a directed poset with respect to the opposite inclusion. So we say that if we have two neighborhoods, we say that U is less than or equal to V if V is contained in U. And it is directed because if we have two neighborhoods, then each of them is dominated by their intersection. So it is a directed poset. Now, if we have a topological space X, then by definition a net in X is just a map, little x, from a directed partially ordered set to X. So here lambda is any directed poset. So in the case where lambda is the set of natural numbers, we just get a sequence in X. By the way, the Russian terminology is a bit different. Usually we say направленность. Иногда говорят сеть, но это не очень распространенная терминология. Обычно по-русски говорят направленность, и это, пожалуй, несколько лучше отражает суть дела. Filtered, okay, let's. Maybe this is. Yeah, in the case of categories, we usually filter it, but of course we can equally well apply the same terminology to posets. Maybe it is better even from the intuitive point of view. Filtered means something like, well. So morally, a net is just a generalized sequence. So usually we use, when we deal with nets, we usually use the same notation as in the case of sequences. So we think of a net as a family of elements in X indexed by a directed poset, filtered poset lambda. So X lambda is just X of lambda. So nets are generalized sequences, and just like for sequences, we can define convergence of nets as follows. We say that a net X lambda converges to point little x, or equivalently we say that the limit of this net is equal to x if for every neighborhood u of x there is an index lambda 0 in our set, such that for all lambda greater than or equal to lambda 0, x lambda belongs to U. So literally the same definition as in the case of sequences. The only difference there is that in the case of sequences, this implies that this is equivalent to say that only finitely many elements of the sequence is only finitely many elements doesn't belong to U. Of course, in the case of nets, this is no longer true because the set of elements lambda which don't satisfy this condition doesn't have to be finite. But in any case, the definition is very similar to the case of sequences. And again, a trivial but important example. Let's consider the partially ordered set from example 2. So this is a set of all neighborhoods of a point in a topological space. And for every neighborhood U of this point, choose an arbitrary point xu in this neighborhood. Then it's immediate from the definition that this net converges to U. So it converges to x just by this definition. In a sense, this example is trivial, but it is important because it implies in particular that this example and many other similar in-spirit examples imply that the topology on X is uniquely determined by convergent nets. For example, a point belongs to the closure of a subset if and only if there is a net in this subset which converges to this point. Also, if you have a map between two topological spaces, then it is continuous, if and only if it is continuous with respect to nets. That is, if x lambda converges to x, then f of x lambda converges to f of x. This is equivalent to the continuity of f. Okay, let's now come back to Banach algebras. Suppose that A is, well, not necessarily Banach algebra, a normed algebra. Then, by definition, an approximate identity. An approximate identity in A, usually we abbreviate it as AI, is a net E lambda in A, such that for every element A in our algebra, the net A E lambda converges to A, and E lambda A also converges to A. We say that our approximate identity is sequential if lambda is just this set of natural numbers with the standard order. And approximate identity in lambda is sequential if lambda is the set of natural numbers. And another useful property, we say that our approximate identity is bounded if the set of its elements is bounded. That is, if the following supremum is finite. Well, let's look at some examples of approximate identities. Probably the simplest example is the standard approximate identity in the algebra for little c0. So little c0 is just the same as big C0 on the natural numbers. That is, this is the algebra of sequences of numbers which vanish at infinity. Well, this is about algebra with respect to the supremum norm. Of course, it is not unital, but it has a bounded approximate identity. Let's denote by En the following sequence. The first n elements are equal to 1, and the remaining elements are equal to 0. Then this is a sequential bounded approximate identity. BAI is the abbreviation for bounded approximate identity. Well, indeed, why is it so? If we take an element little a in A and calculate A minus AEN, so what we get is the supremum of AK, where K is bigger than N. And clearly this goes to 0 because of this. And so it is an approximate identity. In a similar way, we can construct a bounded approximate identity in the algebra of continuous and vanishing at infinity functions on the real line. Again, it is not unital. So to construct an approximate identity, we, for every n, we take a function of the following form. So it is identically 1 between minus n and n. It is identically 0 here and here. And it is somehow piecewise linear. So this is En, and it's simple exercise to show that En is a bounded approximate identity in C0 of R. This follows basically by the same argument as here. More generally, we can construct an approximate identity in the algebra C0 of X on any locally compact Hausdorff topological space. Example 3. Let A be C0 of X, where X is a locally compact Hausdorff topological space. So to construct an approximate identity, we let lambda denote the collection of all compact subsets of K. The collection of all compact subsets of K, of X. And this is filtered, directed or filtered poset for the inclusion. Well, indeed, it is. If you have two compact subsets, then their union is also compact. So it is filtered. And now for every such compact subset K, we choose a function ek in C0 of X such that it is identically 1 on K, and such that its supremum norm is less than or equal to 1. Then it's a simple exercise to show that Ek is an approximate identity, is a bounded approximate identity in C0 of X. Of course, it is not sequential. In contrast to example 2, it is not sequential. So it's natural to ask how about the existence of a sequential approximate identity in C0 of X. And here is an answer. C0 of X has a sequential bounded approximate identity, if and only if X is sigma compact. That is, it can be obtained as a union of countably many compact subsets. Another example, example 4. Is it 4? Yeah. Example 4 is the algebra of compact operators. The algebra of compact operators on a Hilbert space. Again, if X is infinite dimensional, then we know that this algebra is not unital. But again, it has a bounded proximate identity, which can be constructed as follows. We denote by lambda the collection of all finite dimensional vector subspaces. Finite dimensional vector subspaces. Say L and H. Again, it is a filtered poset for the inclusion. If you have two finite dimensional subspaces, then their algebraic sum is also finite dimensional. So it is filtered. And now we construct an approximate identity for every such subspace L. We let P lambda denote the orthogonal projection, PL be the orthogonal projection onto L. So it is a compact operator, because L is finite dimensional. Then, again, it's a simple exercise to show that the resulting net PL is a bounded approximate identity in K of H, in the algebra of compact operators. Again, the actual question is about the existence of sequential approximate identities. And here is an answer. K of H has a sequential bounded approximate identity if and only if H is separable. In this case, it's we don't have to consider all finite dimensional subspaces. We can choose any ordered chain of finite dimensional subspaces whose union is dense in H. And the resulting sequence of finite dimensional projections will be a sequential approximate identity. Of course, it's also rather easy to construct examples of Banach algebras which don't have an approximate identity. Here's a non-example. Well, of course, we always have a stupid non-example. We take any Banach space and equip it with the zero multiplication. AB is identically 0. Of course, there is no approximate identity in this algebra. And here is a little bit more interesting example. We consider the maximal ideal in the algebra of continuously differentiable functions on an interval 0, 1, which vanish at 0. So this is a non-unital Banach algebra, and a simple exercise is to show that A doesn't have an approximate identity. Okay, on the other hand, in example 1, 2, 3, and 4, all these algebras have bounded approximate identities, and at the same time they are C-star algebras. It turns out that every C-star algebra has a bounded approximate identity. So we have the following result. Suppose that A is a C-star algebra. Then there exists an approximate identity E lambda in A such that it satisfies the following conditions. Let's denote them AI1 and AI2. AI is for approximate identity. So AI1 is that this sequence, this net consists of positive elements. They are positive, and on the other hand, they are less than or equal to the identity in the unitization of A. So equivalently, this means that E lambda is positive and its norm is less than or equal to 1. And the second condition is that AI2 is that this net is monotone in the sense that if lambda is less than or equal to mu, then E lambda is less than or equal to E mu in the sense of the order relation on self-adjoint elements that we've just defined. In particular, AI1 implies that this approximate identity is bounded by 1. The proof is a little bit involved, but the construction is very simple. We denote by lambda the set of all positive elements in A whose norm is strictly less than 1. And this is our set. It's not immediate that it is directed, but it is. It can be proved by using functional calculus. And our net is just the inclusion map of lambda into A. And this map, it turns out to be an approximate identity satisfying properties AI1 and AI2. Again, this is not obvious, but by using some tricks, we can prove that this is indeed an approximate identity. In the non-unital category. First of all, I'm not sure it is true, but maybe it is true. But anyway, if it is true, I don't see immediately how it implies the existence of an approximate identity. So of course we can choose an identity in each of these algebras. Maybe this is true, yeah. Maybe. The standard proof is quite different. This is just the construction. So what we want to check here is that first lambda is directed, and second this map is an approximate identity. So this is the what is not entirely obvious. Yeah, the key point is almost, because what's the problem here is that actually if we have an arbitrary sister algebra, it is not generally true that we have non-trivial idempotence in our algebra. There are some examples of sister algebras where we don't have idempotence at all. Like, for example, the algebra of, if we take the algebra of continuous functions on the closed interval 0, 1, which vanish at 0. The only idempotent is identically 1.
In this algebra, there's like no idempotence period, not even close to idempotence, and therefore there are no approximate identity. But you can ask whether there are like elements, so their powers converge to something. And if you can pick approximate identity which consists of such elements, then it should be true that they take just a limit of subordinate object plus this always idempotence, and then it will be a filter limit, not of inclusions, but of subboundaries.
Well, maybe, but
Okay.
oh, okay. Well, that's interesting. I don't think it's trivial, but yeah, maybe this is true. Maybe. Okay. So now, when we speak of approximate identities in sister algebras, we'll always assume by default then that they satisfy conditions AI1 and AI2. This is a standard convention in the sister algebra theory. So, from now on, an approximate identity means approximate identity satisfying conditions AI1 and AI2. Well, of course, the approximate identity which is constructed in the proof here is very big. So this set is very big. But in concrete cases, we can often find a much more manageable approximate identity, like, for example, in example 3 or in example 4. And here also a related result, a proposition, if A is separable, then we can always find a sequential approximate identity. And in fact, the converse is also true. Theorem tells us that there exists an approximate identity always, and we can choose in this way. That of course, I don't claim that every approximate identity satisfies these conditions. We don't assume that it exists. It always exists.
If A is C star,
Yeah.
then it also has.
Yeah. Okay. Now, well, let me say a few words about quotients of C-star algebras. First of all, let's observe that in the setting of Banach algebras and the setting of Banach star algebras, the procedure of taking the quotient is quite straightforward. A simple observation. If A is a Banach algebra and I is a closed two-sided ideal of A, then the quotient of A modulo I, clearly this is an algebra, but this is also a Banach algebra with respect to the standard quotient norm given by the following formula. So the norm in the quotient is the infimum of the norms of A plus B, where B runs over I. This is it's a standard fact that it is complete for this norm, and this norm is easily seen to be submultiplicative. And also, if A is a Banach star algebra, and I is a closed two-sided star ideal, so it is stable under the involution, then the quotient of A modulo I is also a Banach star algebra. A Banach star algebra. The involution is defined in the following obvious way. So what happens if A is a C-star algebra? In this case, it's natural to conjecture that the quotient is also a C-star algebra. And this is indeed true, but this is not entirely obvious. And the proof of this fact essentially involves approximate identities. More exactly, we have the following theorem. Suppose that A is a C-star algebra, and I is a closed two-sided ideal of A. Then first of all, it turns out that I is automatically a star ideal. So it is automatically stable under involution. Second, the norm in the quotient of A modulo I, so this canonical norm, can be calculated as follows. So let's take an approximate identity in lambda, an approximate identity in I. Then the norm of the respective element in the quotient, so for every element A in A, the norm of the respective element in the quotient can be calculated as the infimum over lambda of A minus AE lambda. And we can also replace the infimum by the limit here. So the limit always exists and is equal to the infimum. And finally, by using this formula, we can prove that the quotient is indeed a C-star algebra. So the point is that to prove the C-star axiom in the quotient, we have to use this formula. So the original definition is doesn't immediately imply that the C-star axiom holds in the quotient. Okay, so here is a classical example of a quotient of a C-star algebra. If A is a Hilbert space, then we can take the algebra of bounded operators on H and consider the quotient modulo the ideal of compact operators. So the resulting quotient is usually denoted by Q of H, and it is called the Kalkin algebra. So this algebra was first studied by James Kalkin, and it turns out to be a very useful example. It plays an important role in the extension theory of C-star algebras and in the closely related K-homology theory, which is in a sense the dual to K theory. Finally, the final remark for today is about homomorphisms between C-star algebras. So by using quotients, one can show that the category of C-star algebras is, in some sense, it is rigid. That is, more exactly, we have the following result. Suppose that A and B are C-star algebras. C-star algebras, and phi is a star homomorphism from A to B. So let's recall that we already know. We already know that it is continuous, and its norm is less than or equal to 1. Automatically. But now we can say more. It turns out that the range of this homomorphism, phi of A, is always closed. It's closed in B. So it is a C-star subalgebra of B. Second, phi induces an isometric star isomorphism. An isometric star isomorphism between the quotient of A modulo the kernel and the image. And finally, the norm of phi is exactly 1, except for the trivial case where it is identically 0. If phi is non-zero, then its norm is equal to 1. So this is just a simple corollary of the fact that every the quotient of a C-star algebra is a C-star algebra. Well, indeed, we just factorize phi through the quotient of A modulo I. This is phi hat. So A over I, this quotient is a C-star algebra, and phi hat is injective. Phi hat is injective. But we observed at the previous lecture that an injective star homomorphism is always isometric. So its range, the range of phi hat is closed because it is isometric. but the range of I hat is the same as the range of phi. So the range of phi is closed. And also, since phi hat is isometric, its norm is 1, but the norm of phi always is, the norm of phi and the norm of phi hat are the same. So the norm of phi is exactly 1. Okay, so that's all for today. Now I can promise that the next lecture will be lost in this series of this introduction to sister algebras, of our survey in sister algebras. So we'll discuss positive functionals, the GNS construction, and the tensor products of sister algebras. So this will be next time, and after that we begin discussing K-theory.